properties of liquids. So again, in a previous chapter we talked about the properties of gases. There's no interaction between the molecules, not much anyway. We ignore it if there is, it's so small. And we'll have to get to solids too, but properties of liquids, they're particularly interesting. Properties of liquids, again, molecule to molecule, here they're touching. So they definitely have intermolecular forces. They definitely have those van der Waals forces. And so all of these properties are going to result from considering which types of van der Waals forces it has and what their effects are. And the easiest way to go through this is just do a list here. Number one, viscosity. Viscosity is defined as the resistance to flow. Right? So if I take a glass of water and I pour it out, it comes out pretty easily. It flows easily. If I take a big old glass of, say, maple syrup and pour that, or worse yet, how about molasses, and try to pour that, it's going to be very slow and finally comes out in a big thick kind of, it's very thick as we say, it's very viscous is the correct terminology. It has a high viscosity. It resists flowing. It doesn't just flow out really smoothly and easily. Right? Thicker oils would have a higher viscosity as well. They don't flow, where you can have thinner oils too, though, that flow pretty nicely. Right? So viscosity, the resistance to flow. Water, low viscosity. Syrup, high viscosity. Well, it's all going to be due to the intermolecular forces. Right? If it flows easily, boom, they can slide right past each other, these forces. Or if it has high viscosity, they're slower to flow past. The size and the shape for London dispersions, whether they have H bonds or not, dipoles, that's all going to contribute to this idea of does it flow well or not. Right? So viscosity. The actual unit for viscosity is called a centipoise. Not that we're going to use it, but just to let you know, a centipoise. That's a strange unit that most people haven't heard of. Number two on our list, cohesive forces, another property of liquid. Cohesive forces are simply the van der Waals forces between molecules that are the same type. So a water molecule to another water molecule, how do they attract to each other, right? And what does that lead to? Those are called cohesive forces. And an easy way to think about and see the effect of cohesive forces is in droplets. You know, if I spill some water on a table, it'll form droplets. If this is my table, it'll form this droplet that goes up and comes back down. This little dome, right? Little droplet. They got this. They kind of got a picture of it here. Here's the water molecules, and you see this kind of curved surface here. So it's going to form this little droplet. Why? Well, because the water molecules in that droplet are being attracted to the ones below it. And as it comes off to the side, they're being attracted inward. So you got this downward and inward sort of a force because of the van der Waals forces here. They're not being attracted up to the air, right? But they're being attracted down to other molecules of their own type. And so those are cohesive. If you have fairly strong cohesive forces, then it's going to form a really nice, well-defined drop. If you have a liquid that's not so much like that, right? Like if you spill water, you get the droplets. If you spill like a real thin oil, you're not going to get necessarily droplets. It's going to spread itself out really thin, very thin layer. It's not going to form these little droplets. Acetone kind of does the same thing to somewhere in the middle effect anyway, where it spreads itself out. It doesn't form these droplets. If you spill mercury or some liquid like that, or water, like I said, you're going to definitely get droplets forming. Some have stronger cohesive forces, other ones don't. All right, that makes sense. Number three, surface tension. These are a type of cohesive force, but specifically right at the surface. All right, so we're not necessarily talking about a droplet here. We've got a larger body of this liquid, and so you're looking at the surface of the liquid. And what does that look like? All right, and so the book has this picture with these same arrows. I don't really love that picture here. I prefer this one. Now, here's an example of one of these bugs, these spiders that can literally walk on top of the water. They call them Jesus spiders. Right? They can walk on the water. You and I can't walk on the water, right? But these spiders, these little insects can. They don't weigh a whole lot, but still you think, why don't they just go right down into the water? How is it they're able to actually walk? And they're not floating. This is not a matter of displacement of water, and it's not like a boat. They don't penetrate that water. They're literally on top of the water, right? So why don't they pierce that water and get down in it? Well, because of cohesive forces of those molecules right at the very top layer. Okay? They have strong intermolecular cohesive forces, one to each other going across, right? And if you try to push on those, if you stretch them, right, you're either going to break those cohesive forces, or if you don't push them enough, they'll be intact. You might bend them down and kind of depress them like that, so they're like this, but you won't break them. It just depends on how heavy you are and how strong those cohesive forces are. So here's my picture of this kind of thing where you've got the water, here's the surface, and here's the foot of the insect, right? If it's pressing down just a little bit, it's pressing down on it, it's making this little depression, but the cohesive forces between those water molecules are strong enough that we actually don't break them. Right? And so the spider literally walks on top of the water molecule. Cohesive forces of water, with all those H-bonds and the network that they form, are pretty darn strong. Not only can a spider, but you can actually get like a paperclip to float on top of water. If you lower it down very carefully, you can actually get it to float. Metal floating on the water. And it's not, again, I shouldn't say float, that's the wrong word. It's literally resting on top of the water. It's not a displacement thing, it's a surface tension thing. So it's pretty cool. All right, number 4. Adhesive forces. So if cohesive forces are between molecules of the same kind, adhesive are between two different types of substances. Right? So for example, what adhesives like glues, well, yeah, they're gluing from the glue molecules to whatever you're trying to glue together, wood or plastic or whatever it is. Right? That's why they call them adhesives, right? Adhesive forces are also seen like in the meniscus. You used to see that in the burette in the lab, or the pipette. Get that meniscus right in the line. The meniscus forms that smiley face, and we always measure it at the bottom of that smiley face, right, with water. Here's a picture of that on the right side of this diagram here. There's a pipette, and it's showing that meniscus. Why does it do that? Why isn't it just straight across? Why does it form this smiley type face? Well, the answer is adhesive forces. The water molecules are actually being attracted to the glass molecules. There's an attraction there. Van der Waals force is at work here, right? So because of that attraction, in the middle, it's not contacting the glass, and so gravity's pulling it down. Right at the edge where it gets to the glass, then it's being attracted to it. And so it actually sticks, it adheres to those glass walls. And so what happens is you get this sagging sort of effect. You got that surface tension as well that's also part of this phenomenon, and so you get a smiley face because the water is literally adhering to the glass, and you get a meniscus formed. Makes perfect sense. It's just intermolecular forces. Hey, on the left side of this figure, they actually show mercury. Mercury has no attraction, in fact, a repulsion to the glasses, and so it does just the opposite. Actually, it's being repelled, and so it's actually pushing back, and it actually domes. You actually get an upside down meniscus, if you will, with mercury. Right? So again, goes back to the intermolecular forces, and adhesive forces are those between different types. Finally, in this section, number 5, capillary action. Capillary action is similar to adhesive forces in the sense that it's between two different types of molecules, but capillary action specifically refers to that ability of, say, a liquid to travel upward against gravity, right? Travel upward like into a paper towel or into a wick if you got like an oil lamp, or sometimes, you know, like if you got like a plant, a flower, a tree, or whatever, and how does that water actually get right up there? It's capillary action that brings it up from the ground all the way up. That's capillary action. Here you've got an attraction between those water molecules and whatever this substance is, whether it's a paper towel or the stem of a flower. Right? You've got an attraction, and so the water molecules are attracted up, and then they go up higher, and then up higher because they're continually being attracted upward and upward, and so they're climbing up against gravity even. Right? Well, those are just intermolecular forces again. The adhesive type forces, where they're allowed to travel through. It's not like a solid glass. They can make it through the paper towel or through the stem, and so they travel upward. Right? Wine going up a paper towel, as the book uses as an example in its figure.